In this video, we look at the spectrum of the angle modulation for some pseudo signal. The modulated signal has this format: U of t equals AC cosine 2 pi fct plus beta. Beta is the modulation index multiplied by sine 2 pi fmt. And this modulated signal comes from here, where the message is cosine signal, and we do FM modulation. We obtain the modulation index beta by the maximum phase deviation divided by the bandwidth of the message. We have this format for the modulated signal for FM modulation, where the message is cosine signal. I rewrite this signal here. To obtain the spectrum, we need to use the knowledge of Fourier series. Now let's recall the Euler's formula. So e to the power jx equals cosine x plus j sine x. This is Euler's formula. We can see this is the real part and this is the imaginary part. So now we want to write this cosine part into the real part of complex exponential. So I'm going to have real part, AC. AC is a scalar multiplier. This cosine part can be written as the real part of e to the power j. Inside here, the argument here, this is our x. And e to the power jx, that's j here. And bracket, this bracket is our x. So there are 3 layers of bracket here. The first layer is the angle of sine pseudo signal. The second one is the term before j. The third one is the complex exponential. So now we break this complex exponential up. So this is a plus. This has AC here, e to the power j 2 pi fct, that's first term. The second term, e to the power j beta sine, that's 2 term. This term is related with the carrier, and this term is related with the message. In this term, e to the power j beta sine 2 pi fmt is periodic. What's the period? The period is 1 over FM. How do we verify if a signal is periodic or not? We use this format. So if fx is periodic with time big T, we're going to have this relationship for all x. So for all x, if I evaluate function x plus t as shifted by t, I have the same value. So this is the definition of a signal being periodic. So now we want to verify if this signal is periodic with Tm or not. We replace the argument t with t plus Tm, big Tm, and we want to show this equals to this term. Multiply this 2 pi fmt inside to break this bracket up. So 2 pi fmt, small t. In this term, fm and tm multiply together. That equals to 1, because you can see tm and fm, they are reciprocal. That's equals to 1. So this term becomes to 2 pi. Now this is 2 pi. And we know that sine phi plus 2 pi, that equals to sine phi for any phi, right? So therefore, we can remove the term of 2 pi. This equals to this. This signal is periodic. The period is Tm, that equals 1 over Fm. Fm is the frequency in the cosine signal of the message. Next, we're going to apply the knowledge of Fourier series. Pay attention that this signal has the fundamental frequency of FM because the period is 1 over FM. So therefore, the fundamental frequency for this periodic signal is FM. Now, according to Fourier series, any periodic signal, this is periodic signal, can be decomposed as a linear combination of all the harmonics of the fundamental frequency. Therefore, we have this format. This is nth harmonics, and then this nth harmonics is scaled by C of n. This is a Fourier series coefficient. We sum them up. So this is the physical meaning of the Fourier series, and we apply the knowledge into the angle modulation now. Next, let's review how do we obtain the Fourier series coefficient. Here, Ex is the periodic signal with a period T naught. The fundamental frequency is F naught. Ext can be decomposed, the linear combination of all the harmonics. Small xn here, that's a Fourier series coefficient. This is the nth Fourier coefficient corresponding to the nth harmonics. We do integral from one period and take the average over the period. The integrand is the time domain multiplied by the nth harmonics in the format of e to the power minus j 2 pi fn naught t. In this case, the Fourier series coefficient is c of n. The period is tm. That equals 1 over fm. So therefore, 1 over T naught and 1 over Tm is equals to Fm. I choose alpha equals to 0. So 0 to T naught, that's one period. I do the integral. And this is the time domain function. And this equals to Fm 0 Tm. E to the power j, I take the j out, beta sine 2 pi Fm T and minus 2 pi n Fm T. I have this bracket outside and d of t. I'll do variable change. I'll do u equals 2 pi Fm T. Then we can see that du equals 2 pi Fm dt. This integral equals to Fm 0, still 0. Tm becomes 2 pi f m tm and e to the power j beta sine 2 pi f m t become u and minus dt equals 2. You move this portion to the other side. That's equals to 1 over 2 pi f m du. So this equals to 2. And now I can see Fm where Fm cancel out each other. And Fm Tm, that equals to 1. Therefore, this integral becomes 1 over 2 pi, integral from 0 to 2 pi, and e to the power j beta sine u minus u and du. This integral does not have analytic solution. We have to integral numerically. And this integral is Bessel function of the first kind order of n. This signal, e to the power j beta sine, can be written as Fourier series expansion form. Fourier coefficient is j and beta. Now we plug in this term into the expression of u of t here, this portion by the Fourier series expansion term. This is exactly what I did here. This is the Fourier series expansion term. I have a bracket here. And now this summation is based on n. this is constant, is not function of n, I can take in this term into the summation. Take this in into the summation. I can combine the complex exponential with this complex exponential. That becomes e to the power j 2 pi fc plus nfm t. And the coefficient j and beta still here. EC still here. Real part still here. Complex exponential. If I take the real part, what do I have? I have cosine portion. Now we can have this expression. U of t equals to summation of all cosine signals. And this cosine signal contains frequency fc plus nfm. And n is running from minus infinity to infinity because Fourier series expansion, n is running from minus infinity to infinity. Angle modulation contains infinite cosine signals, frequency running from fc plus fm and fc minus fm and fc plus 2fm, fc minus 2fm, and all of this go on. The bandwidth is actually infinite because if we look at this frequency components, it contains fc plus fm, 2fm, up to fc plus infinite integer fm, and then fc minus infinite fm. This is integer, infinite integer. So you can see what's the bandwidth? The bandwidth will be infinite. Now let's look at the Bessel function in detail. We know that Bessel function does not have analytic solution for the integral. So we need to evaluate the integral numerically using tables or using other software. And in the formula sheet, we provide a Bessel function table. Let's see how to use this table. In this table, we have the value of beta. Those are beta values. Those are positive. This value, 0, 1, 2, 3, these are integers. These are the value of n. The Bessel function is determined by 2 dimensions. And you may find that this table does not provide any values of n which are negative. This is because we have this relationship. And if n is even, we have j minus n beta equals to j n beta. This is the same thing, j n beta equals to j minus n beta. So now, for example, n equals to minus 4, then j of minus 4, 10, and beta equals to 10, for example, that equals to j 4, 10. So let's see what this equals to. In this case, beta equals to 10. That's this column. And n equals to 4. So n equals to 4, that's this row. And this equals to minus 0.22. Okay. If n is odd, then j minus n beta equals minus j n beta. For example, n equals to minus 3, then j minus 3, 10 equals to minus j 3, 10. In this case, that equals to, let's check it out here. So n equals to 3, that's this row, minus 0.06. So we can use this relationship to find the Bessel function values for n is negative. The value of the Bessel function go on here. The table only listed up to the value in the 4th decimal, here the 4th decimal. The values smaller that didn't list here. For a given beta, For example, beta equals to 6, yeah, or beta equals to 8. With n increasing, with n, the value of n becomes big, the value of Bessel function becomes very small. The value is smaller than the fourth decimal, so it's not listed in the table. Especially for the smaller value of the beta, when n is big, the Bessel function values is smaller. But for bigger beta, for example, beta equals to 100 or 150, we can see the value spread out for bigger value of n as well here. The value should go on beyond n equals to 51. Those values are not listed in the table due to the size of the table. Now let's do a recap. For the modulated FM signals, where the message is cosine, which is a pseudo signal, using the knowledge of Fourier series, in the modulated signal can be decomposed as infinite cosine signals. The cosine signals have frequency of FC plus N FM. FM, that's the frequency of the message. And N is running minus infinity to infinity. The magnitude of this cosine is AC multiplied by Jn beta, and Jn beta, that's the Bessel function. Theoretically, the bandwidth of the modulated signal is infinite. However, in practical system, we cannot occupy infinite bandwidth. So we want to define the effective bandwidth. We want to look at the power of the modulated signal. This is the original modulated signal. This is from equation 4. The transmitting power for this modulated signal is simply AC squared divided by 2. And from the derivation of using Fourier series, the transmitting power contained in this message is from equation 5. That's from this equation. That's equation 5 here. So the power contained in equation 5 of this infinite sum of cosine signals, the power, I call it P5, P equation 5, that equals to summation of n is running from minus infinity to infinity. And then for each cosine signal, that's the magnitude squared divided by 2. So that's the power in equation 5. We know this is power for equation 4. Equation 4 that equals to AC squared divided by 2. So if I do infinite sum, I will obtain this theoretically can be proven that should equals to AC squared divided by 2, and this equals the power in equation 4. But if we do the summation from minus infinity to infinity, then the bandwidth of the signal will be infinite. In practice, we cannot occupy infinite bandwidth. So what I'm going to do, I'm going to truncate this sum. I'm going to generate another signal, U of t bar equals to summation of n equals to minus k to k. And AC Jn beta cosine all of this. That's the same thing. I'm not going to write here cosine and here. And this portion goes to here. So therefore, I'm going to have a power P bar equals to summation from n minus k to k AC squared Jn beta and divided by 2. For the definition of effective bandwidth, I want this P bar greater or equals to 98% of the power in equation 4. this is equals to 98% of AC squared divided by 2. So this is a definition of effective bandwidth. I have written here as well. Basically, that's what I explained here. Instead of infinite number of cosine signals, we want to contain limited number of cosine signals from minus k to k. In this case, how many cosine signal I'm going to have? I'm going to have 2k plus 1 cosine signals total. Now, in this 2k plus 1 cosine signal, what's the power? I sum them up, right? So I sum them up, n equals from minus k to k and magnitude squared. I want this power, truncated power, captured 98% of the legitimate power, which is from equation 4, which is AC squared divided by 2. And then if we look at this two relationship, AC squared divided by 2, AC squared divided by 2. So really, we want this relationship, summation of J and beta squared. N is running from minus K to K. We want it greater or equals to 98%. That equals to 0.98. So in this case, we captured 98% of the power, and we do not occupy the infinite bandwidth. So this is the concept of effective bandwidth. Now let's look at an example. In this example, the carrier C of t equals to 10 cosine 2 pi of ct, and the message is cosine 20 pi t. Then FM, the frequency of the message is 10 hertz, and we use FM modulation, and KF equals to 50. We want to find out what the effective bandwidth of FM modulation. So U of t equals to 10 definition, cosine 2 pi of ct, 2 pi kf, you integral of this cosine signal here, and this equals to 10 here, 2 pi of c, and kf equals to 50, we integral this, and 20 pi out here, so we ended up 5 here. So in this case, we can see here beta, this is the figure of beta, and beta equals to 5. It's really maximum frequency deviation, delta F max divided by W, right? The KF multiplied by the max MT and divided by W, and W equals to 10, and this is a 50 multiplied by 1, so therefore we have 5 here. According to our derivation, the modulated signal can also be written as this format, summation of minus infinity to infinity, AC, J, and beta, cosine 2 pi, and FC plus NMT, okay? And this is the spectrum of the angle modulated signal if the message signal is cosine signal. Beta equals to 5. We want to truncate the sum such that the truncated sum captures 98% of the modulated power. The modulated power is, we look at here, this is cosine signal, the magnitude is 10. So therefore, the modulated power is 10 squared divided by 2, that equals to 50 watts. So we want to find out big K such that the power contains truncated signal from minus K to K, and the power is 10 squared because AC is 10, and Jn squared 5, beta is 5 divided by 2. We want them greater than 98% multiplied by 50. And this is a 50, and this is a 50. We really want this relationship holds. Jn squared 5, I do summation from minus K to K. I want them to be greater than 98%. Now we know this relationship. When n is even, J minus n beta equals to Jn beta. When n is odd, j minus n equals minus jn beta. So therefore, if n is even, I have this relationship, j minus 2 beta equals to j2 beta, j minus 3 beta equals to minus j3 beta. Can use the table in our formula sheet to obtain the value of those Bessel functions here. Because of this relationship, this is summation for minus n and n, they are the same value because you take squared. So therefore, we take double of n equals to 1 to k, jn squared 5, and then when n equals to 0, this term left out. So this, we want this summation greater than equals to 0.98. The value of k determines the number of summations or the number of cosine signals in the modulated signal. Okay, in this case, beta equals to 5, that's this column. And you can see the yellow highlighted box here, and this corresponding to 98% power cutoff. In this case, k equals to 6. If this summation is truncated from minus 6 to 6, and this equals to, let's talk about for n equals to 0, that equals to AC J0 5 cosine 2 pi FCT. Okay. And then when n equals to 1, that becomes J1 5 cosine 2 pi FC plus FM ST, right? When n equals to minus 5 AC J minus 1 5 cosine 2 pi FC minus FM T. And when n equals to 2, we have AC J of 2 because this is a subscript of n. Beta always equals to 5, 2 pi FC plus 2 FM T. And when n equals to minus 2, 5 cosine 2 pi FC minus 2 FM T. And then I'm not going to write out all of them. Let's do last two. 6, 5 cosine 2 pi FC plus 6 FM T. And the last one will be AC minus 5 cosine 2 pi. Truncated modulated signal contains frequency FC with magnitude AC J05 and frequency FC plus FM, the magnitude AC J15 and frequency FC minus FM, the magnitude is AC J minus 1, J minus 15. For frequency FC plus 2 FM, the magnitude is AC J25. In frequency FC minus 2 FM, the magnitude is AC J minus 2, 5. The last two frequencies are FC plus 6 FM. The magnitude is AC J6, 5. And the last frequency is FC minus 6 FM. Next, let's look at the spectrum. For frequency at FC, the magnitude AC J05. So I put the screenshot for the Bessel function table here. As beta equals to 5, that's the last column. And n equals to 0, that equals negative 0.18. So I round it up. Right now, I do the positive frequency and the negative frequency is symmetric because that's a cosine signal, right? So to be able to illustrate because I only have limited space here, I only plot the positive frequency here. So the first frequency is FC, the magnitude J05. J05 is negative 0.18, AC equals to 10, so I need to multiply by 10. So this is equals to negative 1.8. And next is FC plus FM, the magnitude AC J1 beta. J1 beta, that's here. J1 beta, that's this value, is negative 0.33. You multiply by 10. We multiply by 10, that will be negative 3.3. And then next one is FC minus FM. FC minus FM is here. FC minus FM. The magnitude is say J minus 1, 5. J minus 1, 5, we know this J minus 1, 5 equals to minus J1, 5. And this equals to 0.33. So therefore, we have it here, 3.3. Okay, so next frequency is FC plus 2 FM. I'm going to do it here, FC plus 2 FM. J25 is here, 0.05. You multiply by 10, that is positive 0.5. You multiply by 10. Okay, and next is FC minus 2 FM. The next frequency is FC minus 2 FM. The magnitude is AC J minus 25. Minus 25, we have it here. Minus 25 equals to J25. We know because this is an even number of n. And this equals to, that equals to still 0.05. You multiply by 10, that equals to 0.5. Let's do the last one. FC plus 6 FM. So the magnitude is AC J65. J65 is 0.13. So you multiply by 10, that's 1.3. Here, that's 1.3. And here, because of I don't have space here, that's FC minus 6 FM, and that equals to 1.3. Okay, these are all positive frequency. In the negative frequency, we have the symmetry, all of these backs. The bandwidth is here, from here to here. So FC plus 6 FM minus FC minus 6F, that equals to what? 12 FM, and FM is 10, and this equals to 120 Hertz. Now let's review of the Carsons rule. Carsons rule said the effective bandwidth equals 2 beta plus 1 W, and beta equals to 5 in this case, 5 plus 1 multiplied by 10. This equals to this as well. And this shows that Carsons rule to obtain the effective bandwidth agree with the calculation we have in this example here. And Carsons rule applies to any other signals. In this example, we use the cosine signal as the message. And Carsons rule to apply to any other kinds of message signals. The effective bandwidth always equals to double of beta plus 1. multiply the bandwidth of the message. So therefore, to obtain the effective bandwidth, we only need to obtain beta modulation index and the bandwidth of the signal for any other signals. But for a special case, when the message is cosine signal, we can obtain the exact spectrum. We can use the 98% power cutoff rate, and we can justify the bandwidth is indeed 120 hertz, which agrees with Carson's rule.